Hello everybody. So in this tutorial video we will have a look at a more uh, complicated simulation. Essentially we will have a cancer cell that can differentiate into different types of cancer cells, those that do only proliferate and those that do mainly migrate. And this is an interesting simulation from a research point of view because we know that cancers are very heterogeneous, and so this tutorial will be a first step towards creating simulations, mechanistic simulations that can be used to better understand the dynamics of cancer growth, and then ultimately also how one could optimally treat this kind of cancer. So this is another future outlook for this kind of research, is to essentially simulate the impact of treatment and to optimize the impact of, or to optimize the types of treatment that one can leverage, like for example radiotherapy or different kinds of medications. So we will have a look at this example, and this will be like a milestone to show that you can create your own simulations that support similar kinds of features, and that will be a good conclusion of this tutorial series of videos. Now we are going to have a look at this example of cancer growth where we have two different types of cells, cancer cells. So in this case we have cells that proliferate and cells that migrate, because also in the growth of cancer we know that these cancers are often heterogeneous, and so quite complex dynamics can occur. So here in the source folder of this project that I created, we have 4 different files. One file defines the biology module, so essentially what the cell does. Then we have these scripts that define the simulation itself, and here we have the script that defines the new cell type that we have implemented. So let us have a brief look at these scripts. Here you see that we import the BioDynaMo standard library. We import the cell type that we defined. We will look at it later, and also the biology module, because this is what we need to define our simulation. And then we have this standard function that we already before had in the previous examples, where we define the simulation parameters in terms of size of the simulation space, and then we define here, we create here an instance of the resource manager. And now here we have a cell. We define a single cell, this custom cell type, at the location of the origin 000, and then we associate this cell with a certain phenotype. Now I will go into this later, but the phenotype here means that it specifies what cell type it is, and in this case we just say it's cell type 1 for the sake of simplicity. Then we assign a certain diameter, in this case 17. Then we also assign a cell color value. So in ParaView, as you have seen before, one can have cell colors, and depending on the range, or depending on the color map, we have different colors. Now for the sake of simplicity, I simply included number 7. We could have any arbitrary number there. And we add then the biology module to this cell. Here the threshold for the volume at which the cell divides is defined, which is the volume of a cell with a diameter of 27. Actually, my colleague Vasilis Vaforakis has contributed some parts here. That's why I have here quite specific values. And then we here have the rate of volume growth per time step. So we have defined this cell, we have associated it with certain features, we have added the biology module, and then we add this cell to the resource manager or to the simulation. And then we run the simulation for 3000 time steps. And afterwards, we output the number of simulation objects. In this case, we only have cell bodies, so therefore this will give us the final number of cell bodies. And then we confirm here that the simulation has been executed correctly. Now, if we look at the biology module definition, so here we have we define our custom biology module, which extends the previous standard base biology module, and it here has the standard constructors that we have in BioDynaMo to define how to instantiate such a biology module, and also what happens in the case, for example, of a cell division. So the threshold is kept. So we inherit the threshold, the volume threshold at which the cell divides, and we also inherit the growth rate at which the cell grows at each time step. And now the really interesting bit is here, the run method. So here we first confirm that the cell where this biology module is in, that this is a micelle object. So that it is indeed this cell type that we have defined. And if so, then we check whether it has a phenotype larger than 0. So we essentially check whether or what kind of type of cell it is. And then if it is indeed a phenotype with larger than 0 value, then we check whether it is smaller than the threshold, so whether the volume is smaller than the threshold we have defined at the beginning. And if it is smaller, then we increase its volume. But if it is not smaller than the threshold, then then it divides. And in the case that this condition is not fulfilled, so that the phenotype is actually 0 or smaller than 0, then the cell does not proliferate, so it does not divide, but what it does is it randomly moves around, and then it also, so this random vector that is defined here is added to the position of the cell. So this is why it's moving around randomly. We could here actually increase maybe the movement, the size of the movement, just to have a bigger impact on the simulation. And then let us look at the custom cell type. So here we define our custom cell type, which again extends the standard cell class. And then we have here the constructor. Now here, what we do is we define what happens in case we have a cell division. So what happens with the cell in case it divides. So here we check if the event that takes place is a cell division event, then we create a random number. So this is a random object, and we can draw a uniform number from this with a distribution which is distributed between 0 and 1. And if this number is indeed smaller than 0.2, then nothing really interesting happens. So in that case, the phenotype of the daughter cell is the same as the phenotype of the mother cell, and also the cell color is the same as the one of the mother cell. However, if this random number is larger than 0.2, so with an 80% chance, then the phenotype becomes -1 and the cell color becomes 3. These are just arbitrary values. But if you remember before, we checked whether the phenotype is larger than 0 or not. So in this case, this would become a cell type that does not proliferate, but it randomly moves around. So this is really where the differentiation process takes place, probabilistically. And then we have these standard getters and setters and the event handler defined. So standard functions that we need to implement. And so that's it, essentially. Then I've also defined the output for the visualization. So at each time step, it outputs the phenotype, diameter, and cell color. And now we can have a look at what that produces. So maybe just to briefly summarize. So we have our script where we define a single cell which proliferates and randomly differentiates because of this cancer behavior, and we simulate this for 3000 time steps. So let us now have a look at the visualization of this, or let us first run and build and run it. So we have built it, there was no error message, and now we run it. Okay, so you have seen here now that we have the final number of cells outputted, about 1500, and it was done successfully. Now, because of the randomness, if we do this again, I expect that we get a different cell number. Let's just confirm this. You see we have a slightly different cell number because at each time step we draw random numbers, and this can be always different, of course, because it's truly random. We could make it reproducible in the sense that exactly the same values are drawn by using a certain seed, but we don't do that here. So that's what we get. Now in this case we get 1000 cells at the end. Now let us visualize this using ParaView now. So we go again to load state, and we select the PVSM file, and we can here actually use for the coloring also just phenotype, because the important thing is that the colors are different. It doesn't really matter what exactly the values are, because we want to visualize that the cells look different. Yeah. So you see here that the red cell here is in the proliferative state, and the blue cells are in the random displacement state, so they're just randomly moving around. Now we have two cells that do not move, that simply proliferate. And as you remember, the migratory cells don't divide. So you see some quite interesting structures emerge from this. So we can go on like that. So there is no need to now really look into this in much more detail here, but if you can create this kind of simulation now yourself and then play a bit around with those parameters, like for example, you can, as I did, change the magnitude of the displacement vector. You can change the probability, for instance, of differentiation. You could even add a new differentiation mechanism where cells that migrate again become proliferative after certain with a certain probability and so on. So there are really a lot of things that one can change, and you get different kinds of final structures afterwards. And I think that this is a nice milestone for your first cancer simulation using BioDynaMo. If you can create this kind of simple heterogeneous cancer structures, and we can take it from there afterwards. Thanks for your attention, and I hope you have fun playing around, and please don't hesitate to get in touch and to ask questions if there are any issues. Thank you.